Welcome to the second part of our lecture series on superconducting resonators. This series is brought to you by the NYU Nanolab, the Laboratory for Quantum Materials and Devices. We would also like to give special thanks to the NordTech Hub and the Microelectronics Commons for making this lecture series possible. In this presentation, we continue our analysis of lumped element resonant circuits. In particular, we'll focus on deriving compact expressions for the magnitude of the input impedance, which we'll later use to connect their behavior to transmission line resonators. We'll also look at two key metrics for evaluating resonator performance: the quality factor and the fractional bandwidth. We have three main learning objectives for this session. First, we will analyze the behavior of the RLC models near resonance. Second, we will derive compact expressions for the input impedance of these models near the resonant frequency. And third, define the quality factor, Q, the fractional bandwidth, BW, and derive their relationship. In the previous session, we showed that for both parallel and series RLC circuits, the input impedance is purely real and equal to R at resonance. Let us now study the behavior of the module of Zn as we move away from resonance. One way to study the trend of input impedance with respect to the frequency is by looking at the sign of its reactance as the frequency approaches resonance. For simplicity, let us start with the series RLC. Its input reactance, Xin, is equal to omega L minus 1 over omega C, which we can rewrite like this. We can express L as a function of omega 0 and substitute it in the expression for the reactance. This arrangement gives us the possibility to study whether the reactance is positive or negative for frequencies above and below omega 0. For this series RLC circuit, we can see that, below resonance, the reactance is negative, which means that the circuit tends to behave like a capacitor. Therefore, the magnitude of its impedance decreases as the frequency increases. Above resonance, Xin is positive, which means that the circuit behaves like an inductor, so the magnitude of its impedance increases with frequency. A similar analysis of the parallel RLC shows that below resonance, its reactance is positive, meaning it behaves like an inductor, and the magnitude of its impedance increases with frequency. Above resonance, the reactance becomes negative, meaning it behaves like a capacitor, and the magnitude of its impedance decreases as frequency increases. So far, we've used circuit theory to demonstrate electrical resonance through equations, showing that both RLC models produce a sharp response at resonance, but in opposite ways. In our analysis, we focused on input impedance as the response, though we could have chosen other circuit parameters. We chose the input impedance deliberately, because next we'll work on approximating it near resonance. This approximation will later allow us to model transmission line resonators as series or parallel RLC lumped element circuits. Let's start with the series RLC circuit. We'll define the input signal frequency as omega 0 plus delta omega, where delta omega is small compared to omega 0. Next, we factor out j omega L from the imaginary part of the input impedance, substitute the product LC with 1 over omega 0 squared, and simplify the term in parentheses as shown here. From there, we expand the numerator and, using our frequency definition, this numerator is approximately equal to 2 omega times delta omega. This leads us to the result shown in the red box. Near resonance, the input impedance of the series RLC circuit is approximately R plus J2 delta omega L. Now let's carry out a similar analysis for the parallel RLC circuit. As before, we define the input signal frequency as omega 0 plus delta omega, and substitute this into the input impedance expression. Next, we factor out j omega dash 0 L from the denominator of the second term, which allows us to apply the binomial approximation and rewrite the term highlighted in red as shown here. Then we combine the two terms highlighted in blue and substitute the product LC with 1 over omega 0 squared and vice versa. This leads us to simplified approximation for the input impedance highlighted by the red box. These two compact formulas of the input impedance as a function of delta omega will be the key for linking these RLC models to transmission line resonators. Before continuing with our analysis of the RLC resonators near resonance, we need first to introduce a parameter known as the resonator's quality factor, which in simple terms is a measure of how well energy is preserved within the resonator. High Q means lower energy loss, low Q means higher energy loss. The quality factor, or Q, is defined by this expression. As we've learned, in an RLC resonator, the stored energy oscillates back and forth between the capacitor's electric field and the inductor's magnetic field. In this definition for Q, the numerator represents how much energy the system stores per oscillation, while the denominator represents the energy lost per second. That's why the formula includes omega. It converts the loss from per second to per cycle, making Q a dimensionless parameter. Physically, a higher Q means the oscillations persist for longer, while a lower Q means they die out more quickly. Resonator loss can come from conductor loss, such as resistive heating in conductors, dielectric loss, such as absorption in insulating materials, radiation loss, such as energy leaking as electromagnetic radiation, and external coupling, which is loss into attached circuits or measurement equipment. The first three losses mechanisms are directly associated with the inner characteristics of the resonator and are usually referred to as internal losses, while the fourth one is an external loss mechanism, typically related to the coupling of the resonator to its feedline circuit. The total loss is the sum of these two major categories. If we take the total losses and divide them by the average stored energy, we arrive at a parallel sum expression for the quality factor that accounts for all sources of loss. This relation, 1 over QL equals 1 over QI plus 1 over QC, is fundamental for quantifying losses in resonators and serves as a useful comparison metric. Here, QL, or loaded Q, refers to a resonator connected to an external circuit. This is the value we measure in practice, since the resonator is always coupled to our measurement equipment. QC, the coupling quality factor, is typically set by design. Knowing both QL and QC, we can then calculate the internal quality factor, QI. In future sessions of this lecture series, we'll focus on how to actually perform these measurements for superconducting coplanar waveguide resonators. In the RLC resonators, the average energy stored is the sum of the magnetic energy in the inductor, Wm, and the electric energy in the capacitor, We. As we learned, internal losses can be caused by conductor losses, dielectric losses, or radiation losses. Although they arise from completely different physics, in the resonator analysis we can lump them together into R, because, from the resonator's point of view, all of them do the same. They remove energy per cycle. Therefore, at resonance, the QI can be expressed as a function of omega 0, R, C, and L, as shown in these equations for both configurations. Let us now express the product RC for the parallel circuit as QI over omega 0 and L as QI times R over omega 0 for the series circuit, and use the compact input impedance approximations to express Zin in terms of QI. It is also convenient to write down the admittance of the parallel circuit since it will be useful in our subsequent analyses. These expressions of the input impedance as a function of delta omega and QI are key in establishing the relationship between the internal quality factor and another resonator parameter called the fractional bandwidth, which we're going to explore next. The fractional bandwidth, BW, is the frequency span between the two half-power points in the resonance curve, normalized to the resonance frequency. For now, I am just going to ask you to accept that the module of Z in at half power is equal to these values for both circuits, but we will demonstrate it later at the end of this session. We continue our analysis of the BW by realizing that we can define the upper half of BW as a normalized delta omega, and, using the compact expression for the input impedance, we can show that at the upper edge of the bandwidth, Zin takes the following forms for both circuit models. Using the values of the module of Zn at half power from the plot, we calculate that the square of the module of Zn at the upper edge of BW is equal to r square over 2 for the parallel circuit and 2 times r square for the series circuit. And from the compact expressions for Zn, we obtain that for both cases the fractional bandwidth BW is the inverse of Qi. Let's take a moment to review what we've covered in this session. We saw that near resonance, we can use delta omega to derive compact formulas for the input impedance. We also learned that the quality factor, Q, measures how well a resonant circuit retains energy, and that resonator losses can be grouped into 2 types: internal and external. We also defined separate quality factors, Qi for internal losses and Qc for coupling or external losses. The total or loaded quality factor is given by the parallel sum of Qi and Qc. In practice, we measure QL, and with knowledge of Qc, we can then extract Qi. Lastly, we learn that the fractional bandwidth, BW, is the span between the 2 half power points of the resonance curve, and that it is the inverse of the quality factor in the near resonance regime. Thanks for watching. The next slides simply show the detailed derivations of the input impedance at half power. We've included them here for completeness. We first recall that the average real power delivered to a load is equal to 1/2 the real part of the product of the input voltage by the conjugate of the input current. We can then use the circuit impedance or admittance to rewrite this formula for both RLC circuit models as shown here. At resonance, the input impedance in both circuits is equal to R, and the input admittance is equal to 1 over R. Therefore, the average power at resonance for both circuits is reduced to these 2 equations, 1/2 I squared R and 1/2 V squared over R. We define the half power points of a resonator as the frequencies where the delivered power falls to half of its value at resonance, in other words, P half equals P omega 0 divided by 2, which translates into these 2 equations for both circuits. We can now use the formula for power to determine the magnitude of the input impedance at the half power points, which gives us the following results. In the parallel circuit, the module of Gn for half power is R over the square root of 2, and for the series circuit this is equal to R times the square root of 2. Thanks for watching, and see you in the next session.